Good morning, my dear students. Welcome back to our new lecture, our new chapter in the optical system course. Now we are in chapter number 5 or lecture number 5 under the name laser oscillation and amplification. Basically, this is one step before the course termination. Our course will terminate by lecture 6, which is Gaussian beam. The last lecture will be in this course, will be delivered in academic weeks 10 and 11. Now in academic week 9, we are interested in the formulation of laser. In the previous lectures, my dear students, we were focusing on the optical cavities, the gain equations, the central theory of laser, what is the conditions of gain, how light is oscillating in a cavity, what is the conditions that should be adjusted in order to maximize the electromagnetic field inside the cavity. How to determine the transparency or the transmission of a cavity, and how can we plot this transmission with respect to wavelengths or with respect to frequency or with respect to the counter or the incremental integer q. Now we are going to sum up what we have did in the previous lectures in order to construct a laser. In this lecture, we will be interested in two famous types of laser, what we can call the 3-level laser and what we can call the 4-level laser, and we will try to make a pure physical and a mathematical description for this system. So let me start now, and I will start actually by using previous slides from previous lecture. Let me first mention that this chapter is demonstrated in Laser Electronics, our main textbook, our main reference made by Verdeen. You can find this chapter in chapter number 8 under the name Laser Oscillation and Amplification. Of course, on the e-learning platform, you will find the lecture slides and also the manuscript, the lecture scripts as well, in addition to, of course, this recorded lecture. Okay, let's now start, and let's start with this equation. If you remember, this was the main equation we reached by the end of chapter 3, the atomic radiation chapter. This equation was used to describe the variation of intensity, I of mu, with respect to delta Z. If you remember, when we make an experiment and when we incident light to a portion of a material and we examine the relation between the output intensity and the input intensity using this rate equation or using this differential equation di mu by dz, and we found that this di mu by dz is equals to some coefficient, we call it gamma. This coefficient, of course, is a function in frequency, as you can see here, due to this lambda square and also due to the line shape function g of mu. So di mu by dz is equal to g of mu multiplied by the input intensity, which is, or the intensity, which is I of mu. So this is a basic differential equation to describe the variation of intensity with respect to distance. Now, in order to have an amplification effect, this gamma term should be greater than 1, so that the output intensity is greater than the input intensity. So our first condition, we have to have this gamma greater than 1. And in order to make it greater than 1, the condition was that N2, which is here reflect the popularity or the density of particles in level number 2, should be greater than G2 over G1, which we consider it as a sum Planck coefficient, multiplied by N1. Here, if you remember, the positive term was indicating what's called the stimulated emission, and the negative term was indicating what's called the absorption. And in order to have an amplification effect, the stimulated emission should be greater than the absorption. If you don't remember these details, so I would recommend to return to the recording of lecture number 3 under the name of atomic radiation. So now, if we apply this condition on the material, again, please remember that this is a material condition. It's related to the popularity. It's related to the population of N2 and the population of N1. So if the population of N2 is greater than the population of N1, then this gamma term will be equals to 1 or will be greater than 1, and then you will have what's called the amplification condition. So this was from lecture number 1. Let's now turn to the next lecture. Of course, sorry, before turning to the next lecture, solving this very basic differential equation, if you remember from mathematics, this differential equation will lead to an exponential term. So we can say that I mu equals to I naught multiplied by the exponential gamma times Lg. And here Lg, if you remember, we use it as the length of the gaining material, Lg. So this is a basic differential equation, a basic solution for a basic differential equation with an exponential solution, as you can see here. So this was the output from lecture number 3, which is the atomic radiation lecture. Let's now turn to lecture number 4, which is the optical cavity. In the optical cavity, while we were defining the photon lifetime, we defined what's called the surviving factor, which is basically the definition of how many photons will survive after one round trip. So when you have an NP number of photons starting in the cavity, by reaching the first border, which is here in mirror number 2, 1 minus R2 of these photons will escape outside the cavity, and only R2 times NB will be reflected. Now, this R2 times NB will travel to the other side and reaching the second border, which is mirror number 1. Now, 1 minus R1 of these photons will escape, and only R1 times these photons will survive. So, after one round trip, when you start with NP photon, you will end with R1 times R2 times NB photons. Accordingly, we define the surviving factor as S equal R1 times R2. Now, we assume that this medium, which is the medium between the two mirrors with the length Lg, this medium is neither a gaining medium nor an attenuating medium. So what effect you have is just the propagation effect, this normal propagation effect, which attribute to the phase of the electromagnetic wave, but does not affect the amplitude either positively or negatively. And this was the main focus of chapter number 4 while we were dealing with the optical cavity, and we will deal with what we can call a lossless cavity. No losses, no gain. But the question is now, what if we insert a gaining medium here? What if the medium between the two mirrors is a gaining medium, which the one we defined in the previous slide? I mean, by moving inside the cavity, the number of photons is somehow increased using this coefficient, which is E power gamma Lg, and it's increasing because, as we mentioned, knowing that we apply this condition, that means that gamma is number greater than 1. That's why we have, gamma is number greater than 0. Gamma is number is greater than 0. So as far as gamma is greater than 0, then this exponential will be an increasing exponential. So now the condition is you have losses. You have losses due to the reflection of the two mirrors, which is totally with one round trip equals to R1 times R2. However, on the other hand, you have gain because you mentioned that the medium between the two mirrors is a gaining medium. Accordingly, you will have a general equation which include both the losses and the gain. The losses is included in the term R1 and R2, which represents the reflection between of the two mirrors. The higher the reflection, the lower the losses. And also there is another gaining parameter, which is E power 2 gamma Lg, and here we use the term 2 Lg to express the distance carried out in one round trip, as the distance between the two mirrors is Lg. So by one round trip you will make a distance 2 Lg, and gamma is the gain coefficient, which can be greater than 1 than 0 if N2 is greater than G2 over G1 times L. So now this new equation, this new surviving factor, describes the losses in the system and also the gain in the system. And in order to make the system, the whole overall system is an amplification system, you need to make this equation is greater than 1. If this equation is smaller than 1, that means that you are losing electrons, you are losing, sorry, photons, because what we say is that we start with NB photons, and after one round trip, we will have S times NP. So, for example, if S is equal to 0.9, then you lose 10% of your photons. Then it's an attenuating medium, because as far as you are progressing inside the cavity, you are losing photons. However, if this S is equal to 1.1, that means that you gain more than 10% of photons. And here we have what we can call an amplification, or between quotation, what we can call an oscillating system. So now this is the overall surviving factor. And in order to ensure that this is an amplification or oscillation, we have to have S greater than 1. And this was the next step, that to put S is greater than 1. And if S is greater than 1, then we will have another condition for gamma, that gamma should be greater than 1 over 2 Lg ln 1 over R1 over and 1 over R1 R2, and we will call these parameters as an alpha. Here we have to stop a bit and start to see. Now, using these 3 slides, we have concluded 2 conditions for a gain. The first condition, my dear students, was in the first slide, where or when we said that N2 should be greater than G2 over G1 times N1. This condition is applied to make gamma greater than 0. And it's a material condition. It does not relate it to the system. It does relate it only to the material, the gaining material, because it's a relation between the population in the level what's called E2 and the level what's called E1. Now, if you have gamma greater than 0, and or in other words, if you ensure that you have an amplification condition, does that mean that you are 100% have an S greater than 1? Simply the answer is no, because you can have an amplification condition. However, the losses may be greater than the amplification. So you amplify the signal from one side due to the gaining material, but due to the losses in the reflection R1 and R2, due to R1 and R2 is not typically equals to 1, which is a hypothetical value. So as far as they are not equal to 1, you have losses, and the losses are dominating. So you have gamma greater than 0, but the overall S term is still smaller than 1. So you are still far from an amplification or an oscillation system. So you need to have another system condition. So we have first a material condition represented in the relation N2 and N1, and you have another system condition, which is that gamma should be greater than 0, but not only greater than 0, it should be greater than 0, and it should be also greater than 1 over 2 Lg ln 1 over R1 minus R2. So these are the 2 conditions you have to apply in order to ensure that your system is working as an amplification system.